The idea is a star, like take our sun, just as an example. Our sun is one solar mass. It's about 1 million miles around, um, and it's got fusion going on deep in its core. And fusion is energy, and that energy keeps the star up from collapsing. You could look at mass as acceleration, how fast mass comes together, with the speed of light being as fast as possible. Um, so what we're going to talk about is gravitation, what gravity actually is, and we're going to start off with quantum mechanics, which basically describes, you've heard of the Hadron Collider. Well, what they're really doing there is they're taking neutrons and protons and they're using a magnetic field to fire neutrons and protons at metals, gold, whatever, atoms. And when you subcool matter down to like absolute zero, that's about as still of a wavelength as you can get. So it's like basically like taking the probability, let's say, of a particle to move like this, and it's slowing it down to its slowest possible amount of time, and they'll fire. And when it hits, a lot of times it makes a more massive particle. Like it'll turn into a fluid, it'll melt, and it'll turn into like a more massive particle. And that's how we know in the upper atmosphere, when protons come from outer space, they get fired out of black holes and things like that. And when they hit the Earth, they actually turn into like something like a muon, a pion, a kaon, and they'll decay. And along with that, with the destruction and decay of a particle, a lot of times you'll release photons and neutrinos. And that's how they conserve energy, is by the mathematics explains it in that type of way, to where nothing really ever goes away, it just turns into something else. But basically, your basic hadron, your proton, your neutron, these things are filled with quarks, and if it's a neutron, it's a neutral charge. It's going to have 2 down and an up. If it's a proton, it's going to have 2 up and a down. When you start with hydrogen, we'll just use hydrogen, that has the proton in it, and that's it. Proton and electron, no neutron. But as you move up the periodic table of elements into helium and heavier elements, you're going to have proton, neutron, or more of those, double, triple, like that, and electron orbitals as well. Basically, the electron is like a huge football field of room, and the nucleus is tiny, like a mustard seed. So when light travels through this stuff, and they'll actually hit gases with lasers and to test them and measure them. They'll use a beam and another beam, and they'll test to see what's going on. And like I said, these are waves of probability. So even the quarks, like I said, there's 3 of them, and they stay together. They're held in by the gluon field, which the gluon field is the strong force field that acts like a capsule to the quark. So that's what keeps your hadron together. But you have baryonic matter, and you have bosons and fermions. If something's behaving like a fermion, that means it's hot, it's moving around, and it's acting like a particle for sure. Bosons, those have a spin of 1, and those are your Higgs, your WZ boson, your photon, your phonons in your brain. That's the bosonic fields. So you got energy and matter, energy and mass. Okay, this star begins to make heavier elements deep inside of it, and what ends up happening is it loses some volume from the weight of its own gravity. The energy can't keep it up anymore. And when that happens, if you have enough mass, if you have 1.4 solar masses will give you a neutron star. If you got 3 solar masses, you could make a black hole. And in that case, the atoms, because we're talking about atoms here, will collapse and melt, all right? And your electron, which has got a negative charge, and your proton, which has a positive charge, will actually join and take each other's spaces over. And when that happens, you get more neutrons, okay? But if you have 3 solar masses, We're going to bypass that degeneracy pressure, is what they call it. And what will happen is you get a full collapse. And at that point, mass is collapsing at just about the speed of light, and there's no stopping it. So what you call matter or mass, just as on the edge of a black hole, the event horizon is the Schwarzschild radius tells you, like for instance, one solar mass will collapse to a 3 kilometer sphere. So you go up from there. If you got 3 solar masses, you're talking like 9 kilometers. So these are very small areas. And it's because they don't have the energy content they used to have. The particles are not going to be able to move around because they're crushed, they're flattened, and you can pack a lot more mass in when you have matter that is at absolute zero. It has no thermal energy value. It just has that intrinsic 0 point energy. The energy of the particle, the entropy, if you will, of the particle is all that's really left. So now, right around the edge of that, the mass, just like, in the wintertime, if you drop a stick in the snow, it might make an imprint. It might even fall in a little bit, displace a little bit. But if you step with your sneaker, the mass of your body will just crush right through that and melt right through that. Well, the black hole is doing that to the matter around itself. And when this gas and dust crashes into this massive body, it heats up and it releases light. And then that light gets trapped actually around the hole. And the hole can actually begin to frame drag. It's got an angular momentum and a spin. And it's so dense and powerful that it starts to warp the space around it. And light photons from behind it and underneath it will actually bend out to the front, and you'll be looking at basically like a 2D picture. So you'll be seeing different parts of time all in the front. And if you entered, like let's say you had an impervious suit and you were just going to enter a black hole somehow, and it wouldn't crush you and turn you into subatomic particles, what you'd see is you'd fall in from gravity at the speed of light, and you wouldn't really experience time. You'd appear redshifted. It would look like you just froze there. But basically, right around the edge of these things is very hot because it's full of photons, and those photons are trapped, and there's Hilbert spaces where photons are traveling in many directions. So matter doesn't really stand a chance there in terms of what the turbulence with energy is going to do to it. So matter starts releasing a lot of its energy as photons, and then those photons are trapped. They have something called an innermost stable orbit, which is the last place you can really move at light speed before you go inside the hole. One of the weird things about them is batteries. If you charge them up, they get heavy. Well, black holes are like this. They have nothing but photon around them, and then they get heavier as they eat the light. So that's pretty weird stuff, something so dense, it eats light and gets heavier. But nonetheless, this is what happens. When we go a little deeper into the theory, I'm talking about quantum mechanics. The Higgs boson, the Higgs mechanism, if you will, the sombrero, the Mexican hat, the place where an axion or dark matter will first cling on to the vacuum of space and actually produce a rest mass, because the Higgs will it's not in an excited state, so it presents a little bit of mass. But with black holes, it might just be that with all that crushing density pushing everything into the singularity, that a throat can actually develop to another universe, and stuff can travel through that. Not you or me, but energy perhaps. Well, this Higgs mechanism that presents a rest mass gets excited. And when you have mass at rest, basically you have a chunk, or you have something you could grab onto. But when you energize this thing starts moving around too much, and it zeroes out its own weight in a way. So it just might be that black holes do this to the Higgs, and they might be feeding energy backwards through time to another universe. Really weird stuff. But if to get a really good sense of what happens here, these atoms collapse, and when they do, uh, protons and neutrons, the components of atoms, will come out, and those will be melted. And when those melt, you're gonna get quark gluon plasma, and that's your hadron components, right? Your proton neutron components coming out almost like lifeblood, right? And now your quark gluon plasma um, can be heated. If you add more energy to it, it's going to release photons and so on and so on, and then the photons can't go anywhere. So your quark gluon plasma and your photon is going to be what you're going to see when you get close to this thing, okay? But if me and you could see it from 2-3 miles away, 10 miles away, and had the ability to not zoom in at light speed and get eaten by it, what you'd see is kind of like a red haze. It would look sort of like a star, but you'd see a red haze, with like energy underneath it. And if you were able to get through that and get to the edge and get to the event horizon, the place of no return, it's inescapable, where it's, you can't exactly penetrate it and fly through it, but you can't get away from it either. No amount of energy, no amount of electromagnetic force, even moving at light speed, you can't get away from it. So you start making your way there. When you get to the edge of this thing, your matter gets ripped apart and you get spaghettified. Okay? If it's a supermassive black hole, that's going to happen a little further inside. If it's with the solar mass hole, it's going to be so turbulent that you're going to get ripped apart before you ever approach the event. But let's say it's a supermassive black hole and we're going to enter it. By the time we get to the edge, it's going to look to anyone watching as if we just got frozen in time right at the edge. But to us, we will go inside it and we will become part of the hole's entropy. We will literally be almost no different than a memory in your brain. Where these are linked in neurons in the brain, okay, there are physicists that believe that the phonons in the brain that deliver a memory might actually be coming from what's called negative time, and meaning that it happens at light speed. It doesn't experience time. There's nothing that can get in the way. There's no way to measure it, and the only person who can observe it is the independent observer. Same with the black hole. If you were to fall into the black hole, no one else could experience that. Only you could. Well, with a memory, it's the same exact way. This energy comes from somewhere where time doesn't exist. And when you think of a thought, it hits at light speed. It never experiences time. But we know it experienced time because it's a memory. We know it's something that happened before, but you're drawing it up in your mind. So black holes in the brain, physiology, physics, they can correlate. But what's so interesting about these black holes is the cluster collapses. Right now, our whole local group and a bunch of other galaxies are all falling towards the Great Attractor. But further out, way out into space, like I'm talking like 7 billion light years away, there's a Phoenix cluster. And this thing, even though its local gravitation is pulling things in, the expansion of space is so fast out there because it's like a wave. At the further out you go, the faster it goes. That this Phoenix cluster is actually floating away at nearly light speed, which is insane to even think about. But it's definitely not falling in the Great Attractor. But our galaxy, the Milky Way, and the one nearest to it, Andromeda, are in an elliptical pattern and they're collapsing. However, space keeps getting bigger. So as space keeps getting bigger, the two keep trying to come closer, but then the network, the grid, the fields keep spreading out. So they're not getting much closer. In fact, over time, since time began, they've gotten about 1/10 the length of Andromeda closer together. And it's going to be billions and billions of years before that will happen anyway. And I mean, just to give you an idea, our sun making its way around the galaxy takes hundreds of millions of years even to go around the galaxy once for our star. So it's only done that one time since the dinosaurs were here. So, that gives you an idea. Our Milky Way flies at 1.3 million miles an hour. So all those accelerations are what gives you gravity. You got the Milky Way moving at 1.3. You've got the sun moving at 500,000 miles an hour around the galactic plane. You've got the Earth traveling around the sun at 67,000 miles per hour. When you add all this up, that's a whole lot of, if you held a soda bottle in your hand and you winged your hand, that fluid would experience a pressure and a force, and that matter would have more force than when it was just sitting still. So the idea with gravity is you have these accelerations and then you have curvature. They have something in science called the parallel postulate, and what it means is Newton knew that if you kick something like a ball, it'll fly straight. As long as it's not acted on by any of the forces, it will fly straight. However, in a curved space, like a skateboarder coming into a pool on one end of the pool, and another skateboarder is coming from the other end, but the two end up at the bottom together. Or you're in the back seat of a car, you're driving forward. You feel a G-force to the back of the car, you're stuck to the seat. The driver banks a right-hand turn, and you and some heavy guy get stuck to the door. Well, that's gravitation. Another example of gravitation would be leaves blowing in a vector flow outside a building, and they come across a 45-degree wall where that mass is going to steal that mass's force, and it's going to get stuck and gravitate. And the more leaves get piled up, the more mathematical chance you have to stop more leaves. This is how matter clumps up. But when you have accelerations that are creating weight, right? This is why when you fly a rocket out of the Earth in time, it looks like you're going on a straight path, but as that Earth turns and accelerates out of that area, that rocket ended up making a curved motion. And they call them geodesics, and what the deal is that when you're in an accelerated frame, you can't tell the difference between proper acceleration and gravity. They're literally one and the same. So a gravitational field happens because of acceleration. So you're on a manifold that's moving you, and when your weight is resting on it, it can move you just fine, exactly where you're supposed to go. When you displace and you lift something up and you let it go, well, now that matter is going to move in curved space. Okay, so just like if two masses were on a track together and they start to come around the corner and they're accelerating, eventually they'll end up coming back together. And so when you add that equivalence principle, the part where you stick to the seat because a race car took off or a rocket took off, okay, and you add that to the parallel postulate, which is that two masses moving like the guys in the pool, okay, when you put those together, you got gravity. Okay, you got masses that can continually come back together. But when you get down to the quantum mechanics level of black holes, it's amazing because technically there's so much weight from mass and the volume has gone down to such a finite level that really all you have there is a memory. And it's not too different than in physiology with the brain, understanding where knowledge, memories, and thoughts come from. Okay? Because they pop out of nowhere. You can think of anything you want right now, and it comes out of where, right? It's not really experiencing time, it happens instantly, you know? So quantum fluctuations near these black holes, this is the last part. Particle and antiparticle pairs pop up in and out of existence. And what happens is they annihilate and photons and neutrinos come out and energy is conserved. Well, near this black hole, accelerations are so bad that sometimes a particle-antiparticle pair can get separated and they're entangled, and that just makes more energy because quarks just pop out of nowhere. Like, if you try to pull gluons and quarks apart, you'll make more quarks, actually. So, the black hole does this, and so this is how energy conserves itself. Um, but yeah, the black holes, they start at 3 solar masses, but just to give you an idea, our Milky Way center, the Sagittarius A there, that thing is 4.3 million solar masses. And then something like in Andromeda's core, there's 100 to 140 to maybe 240 million solar masses. And so when you get a supercluster collapse, like something like the Great Attractor, okay, you're bending the sheet way too much. And now other masses are going to feel that for hundreds of thousands or millions of light years. 150 to 220 million light years away, that's a gravitational distance. Something along the lines of 7 billion to 10 billion light years away, that's expansion distance. So they're never going to be coming back this way. Our stuff is all going to collapse together, but they will be gone. Anyway, I hope you liked the show. That's just one that I want to do on black holes. It's really just touching on black holes, actually. There's a lot more to them, like Hawking radiation, Einstein-Rosen bridges. So there's a lot more to it, but I hope you like